Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, we are in the beginning of topic C, lesson 11, and that is the cone of Mount Etna up close and personal. And we're doing properties of tangents today. So if you sat through my lesson 10 video, which is the longest video I've ever made in the last 6 years that I've been doing this, it was a very lengthy lesson. This one's shorter, 2 pages. So let's do this. Lesson 11, properties of tangents, classwork exercise. CD, segment CD and segment CE are tangent to circle A at point D and E respectively. Use a 2-column proof to prove that A is equal to B. All right, before I get started though, I want to define what a tangent to a circle means. So the first thing I'm going to do is highlight what we're talking about here. So they're saying that CD and CE are tangent. Well, in order for a line to be tangent to a circle, it has to think of a ball sitting on the floor. The ball is tangent to the floor. Or if you put a ruler on an exercise ball, the ruler would balance on it and just touch it at one point. That would be tangent. And the tangent line has to be perpendicular to the radius. That defines a tangent. So if I drew 2 radii, radius AE and radius AD, then they are perpendicular, then I know that CE is perpendicular to EA, therefore CE is a tangent. And if CD is perpendicular to DA, then it is also a tangent. So that is the definition of a tangent. Okay, so the first thing we want to do is draw radii, AD and AE, which I did to explain to you that they are perpendicular to and the definition of tangent. So I'm going to leave those there. Radii AD and AE are drawn, and I drew segment AC. So what I did was I created a line segment from the center to the point outside the circle, and that's what's called an exterior angle. Angle DCE is an exterior angle, and now ACE and ACD are exterior angles. So what's the first thing we're going to do in our proof? Well, we're going to say, let's see. Well, what is CD? First thing we're going to do is say segment CD equals A and segment CE equals B. Okay. And that is a given, obviously. It's labeled CE and B, so there you go. All right, so now we want to say angle ADC and angle AEC are right angles. And that is, then what we say here is tangent lines are perpendicular to the radius at the point of tangency. And rather than me trying to write that, I'm just going to paste it in here. Okay, so tangent lines are perpendicular to the radius at the point of tangency. The point where they touch is called the point of tangency. Okay, and then what we're going to say is, now we have 2 triangles, triangle ADC and triangle AEC are right My pen just went wacky on me. Okay, so triangle ADC and AEC are right triangles, and that's just simply the definition of a right triangle with a right angle. So we say definition of right, oops, 2 words, guys. Definition of right Okay, now we're going to say that AD equals AE. All radii in a circle are congruent. So this equals this, and I label my diagram. Okay. I am now going to say my favorite reason. AC is equal to itself. So this green line is in both triangles. It's equal to itself. That is the reflexive property. Okay, so AC equals AC. And now I can say triangle ADC is congruent to triangle AEC because I have a right angle, I have a leg, and I have the hypotenuse congruent to a leg and a hypotenuse. So that's reason, hypotenuse, leg. What are we trying to prove? We're trying to prove A equals B. Well, since CD equals A and CE equals B, I can now say that CD equals CE. CD's in this triangle, CE's in this triangle, and that's because corresponding parts of congruent triangles are congruent. And then I now can say A equals B, and that's just simply substitution. Okay, so what did we just prove? Well, we proved that if you have a point outside a circle and you draw a tangent to this side of the circle and you draw a tangent to this side of the circle, those two tangents have to be congruent every time because of this proof. Okay, page 2 brings us to number 2. Wait, where's number 1? Number 1 exercise was the proof. Okay, so now number 2, we now have that proof in our arsenal. That is in our toolbox now. Now we get to use it all the time. So now we're going to apply, and this is the fun part of math. Treat this like it is a puzzle, and now we have a new rule to find puzzle pieces. So in circle A, the radius is 9. So the first thing I'm going to do is draw a radius. And how about red? So from here to here, and that is a length of 9 millimeters. I don't like cluttering up my diagram with the unit of measure, so I'll just put a 9. And BC equals 12, that is over here. It says to find AC. Well, AC is not even there, so let's find it. So AC is right here. So from our proof, we know that BC is a tangent because it's perpendicular to, this is a point of tangency. If a radius comes out to a point where a line segment outside the circle is coming to, then that is a point of tangency, and therefore the measure of angle B is 90 degrees. So I have a right triangle. So the measure of AC is going to be the Pythagorean theorem. So I'm going to say 9 squared plus 12 squared equals AC squared. 81 plus 144 equals AC squared. 4 plus 1 is 5. 4 plus 8 is 12. Carry the 1. And I get 225 equals AC squared. And now I'm going to take the square root of both sides. And therefore that is going to become AC equal to the square root of 225, which is 15 millimeters. So there is the answer to A. Okay, B says to find the area of triangle ACD. All right, so triangle ACD is right here. And from our prior proof, this is equal to this. This is equal to itself by reflexive property, and therefore we have hypotenuse legs. So these two triangles are congruent. The tangent from the same point outside has to be equal to the tangent over here. So why did I draw 9? I have no idea. That's a 12. The radiuses or the radii are always equal, so that's 9. So the area of a triangle equals 1/2 base times height. So the area of triangle ACD equals 1/2 the base 12 times the height 9. So that is going to equal, well, half of 12 is 6. 9 times 6 is 54. So it's 54 millimeters squared. Part C, find the perimeter of quadrilateral ABCD. So now they're saying, if I get rid of this now, there is a four-sided figure. It's actually a kite. Quadrilateral ABCD, perimeter equals side plus side plus side plus side. But in a kite, two of the sides are the same. So if I could do this. So the perimeter equals 2 times 9 plus 2 times 12, which equals 18 plus 24, which equals 42 millimeters. And that is our perimeter. Okay. Number 3. Let's see, let's use purple this time. In circle A, EF is 12. That's right here. That is a tangent. So let me just point that out to you using purple and a little bit thinner. So EF is right there. That is a tangent. Well, there's another tangent that goes right there to another point over here, point of tangency D, because if I drew AD, it'd be a radius, and if I drew AF, it'd be a radius. So this over here, oops, forgot to switch back to my pen. I could get away with it with a 1, but not a 2. So this is 12, okay, because of our proof on page 1. Okay, keep going. AE is 13. AE, where's E? Right here. So I need to draw that. It's not in the diagram yet. So make it a little thinner. So the segment from A to E is 13. All right, so let's make that 13. AE is 13. AE is to AC as 1 is to 3. So AE is to AC. Let's draw that. Okay, here's AC. AE is 13, AC is 3 times that. Okay, this is obviously not drawn to scale because 1 to 3, well, if AE is 1, then AC is 3 times that 13, or if AE is 13, I mean, then AC is 3 times that 13, or 39. Okay, so those are all of our givens, except you had to calculate that. It says find the radius of the circle. Okay, well, this whole distance is 13. So in order to find the radius of the circle, keep in mind what we just proved. Okay, I can draw a right triangle here. So this is a right triangle where I have one leg 12, the radius is the other leg, and 13 is the hypotenuse. So to find the radius, I would say a squared plus b squared equals c squared. Write the formula. Substitute the givens. R squared plus 12 squared equals 13 squared. Simplify. R squared plus 144 equals 169. Subtract 144 from both sides and we get 25. And the square root, we need to take the square root of both sides, and that will give us R equals 5. So the radius of the circle is 5. So this is 5, and this is 5 from here to here. So this little piece here is 8, which makes no sense. Okay, obviously not drawn to scale. And if this is 5, then this is 34. Okay. All right, so find BC. Where's BC? BC is over here. Okay, so how am I going to find BC? Let's switch this to, what color have I not used yet? Blue. So I want to find this now. Again, if I draw another radius over here, I have now created another right triangle over here, and I know this is 5. And I don't know what that is I just drew. That sure wasn't a 5. So this is 5. I don't know this, but I know my hypotenuse is 39 in this one. So again, I'm going to write a squared plus b squared equals c squared. And in this case, I don't know BC, which is a squared. So I'll just say BC squared plus 5 squared equals 39 squared. So BC squared plus 25 equals, and I'm going to use my calculator for this one, 39, hello, I hit on 39 squared, enter 1521. So BC squared is now equal to 1521 minus 25, which is 1496. If I did that right, 21 and then 4 more. 1496, that was a good year. So the square root of, and I'm just going to do this just in case I made a mistake, 1521 minus 25, I could do it this way. And was that the same as my square root of 1496? 38.67. So that would, so what I did here was I took the square root of both sides. So therefore, BC, and I'm going to do an approximation now because it's irrational. 38.67, round to the nearest whole number, BC would be 39. Okay, and we're not given any unit of measurement, so I would just say units. R equals 5 units. BC equals 39 units. Part C. Let's switch to red now. Find EC. Where's C? Oh, it's the whole thing. Oh, well, that's easy. We just found BC to be approximately, is that right? 39? It is. That can't be. Oh, I guess it can because it was a little less. Let me explain that. 38.67 is a little bit less than 39. And the hypotenuse has to be the longest side of the triangle. So if I took this value squared plus 5 squared, then I get 1521, and the square root of 1521 is 39. So that is right. So the reason I picked up on that was if this was 39 and this is 39, well, that's an isosceles triangle, so this would have to be 90 degrees, and that's impossible because there's 180 degrees and I got nothing over here. So this problem, I really don't like the numbers they chose because of that. I don't want to confuse you. I'm going to put the approximation over here just so you don't think that that is an isosceles triangle. So I'm going to put 38.68. I'm going to put 38.68 over here. That is not an isosceles triangle. That would be impossible. There's no such thing as a right isosceles triangle on a flat plane. Okay, so let me make that neater. That's a mess. 38.68. So if BC is 38.68, then guess what? BD is the same length. So this is 38.68. So EC equals ED plus DC. And ED is 12. So EC equals 12 plus that 38.68 or 39. So EC is approximately 39 plus 12, which is 51 units. And remember, it's an approximation. Okay, but I did change that from 39 to a decimal because can't have an isosceles right triangle. Okay, page 3 brings us to a welcomed short lesson. review the lesson summary, 2 theorems and some relevant vocabulary, and go do your problem set.